Welcome back. And our last topic here that we're going to talk about in this aqueous ionic equilibrium chapter is complex ions. And we've talked about things that we've labeled as complex ions before. And we had this one where we said, hey, if we take these highly charged metal ions, they're going to be surrounded by water and they'll eventually release some H+. So both of these are considered complex ions. They are a metal center surrounded by some other ligands, but they're aqueous. Right? They're actually still in solution. We've talked also about solids, right? If we talk about, say, lead 2 chloride solid, Pb2 plus 2Cl minus. And we talked about that in terms of the KSP, the solubility product constant. So here we had an ionic compound, the lead chloride, but when it fell apart into ions, and when it combined together, it formed a solid. So it was a precipitate. It went out of solution and kind of formed this separate phase that was no longer part of our solution. What complex ions do is they actually stay in solution. So I'm going to give an example of it, and then we'll talk about other ones as we go along. So it turns out if you take some iron in solution, iron 3+, and you combine it with 6 cyanide ions, it'll form a complex ion, which is iron complexed with 6 cyanides. Now, instead of being a solid, this one's actually still aqueous. And part of the reason it's aqueous is because it's charged. So if we look at the balance of charge here, we have a +3, we have 6 minuses. So this is actually going to be a 3-. Now, most people will put that into square brackets in order to have the 3- outside there, but I'm just going to leave it as is. But you'll see different notations of people doing that. Now, this one, again, it's still a metal center reacting with a bunch of other things, but it's different than KSP because KSP means those things form a solid. Complex ions means those things just form this other complex that is still aqueous. And so these are actually very common in certain types of things. You did a homework we're talking about how carbon monoxide attached to hemoglobin. That's essentially a complex ion. And you also saw that the K on that one, the equilibrium constant, was very, very, very large. And so that's what happens with these complex ions, is these tend to have very, very large K values. And in fact, the K for this guy is 2 × 10⁻43rd. That's an enormous K. That says that that product is ridiculously flavored. Not just like favored, not just like really favored. We're not even talking like, you know, Joseph in the Technicolor Dreamcoat. We're not talking like Joseph. We're talking like favored beyond belief. Okay, so huge amount of favoring of the products over the reactants. So what does that mean? How are we going to do chemistry with that? Well, the first thing we're going to do is we're going to define a new K value, and we're going to call it K sub F, which is complex ion formation. Formation, that's how I remember it. F is for formation. I'm forming it. And it's going to look like this for this particular one, is it's always the complex over the individual parts. And you'll notice that's different than our KSP, which is solubility. Solubility means something falling apart. So KSP is always the complex, the solid, forming the ions. KF is always the ions forming the solid. Little tricky to keep track of, but you got to keep track of the fact that you have kind of different things going on in those two, even though they're somewhat similar because it's a metal attaching to a bunch of non-metal pieces. So we call it complex ion formation constant. And again, this one is huge. It's 2 × 10⁻43rd. And so what we're going to do is we're going to do a situation where we try to put this together and figure out what's going to happen in solution. So we're going to go ahead and put together a solution where we have 100 milliliters of 0.020 molar iron 3 nitrate. And we have 100 milliliters of 1.0 molar potassium cyanide, not thiazide. And what we want to know is what is the final equilibrium concentration of Fe3+. That's what we want to know. Now, it's very tempting to be like, well, let me set up an ice table, right? I've got some concentrations, I've got a K value. I'm just going to set up an ice table and see what I get. But it turns out, if you remember, when we were talking about titration, we said, hey, look, when you've got H plus in reaction and there's something for that H plus to react with, the H plus reacts so strongly that it's not an equilibrium problem. It's a one-way problem. And so what we did in those cases is we did the one-way problem. We did the strong acid reacting with something or the strong base reacting with something. And then when all the strong acid or all the strong base was gone, then we did the equilibrium problem, right? When all the powerful things are passed, then you can figure out what's going on. Since we have a K here of 10 to the 43rd, that is an enormously powerful, strong driver towards the products. And so if we start with a bunch of reactions and we say, hey, I'm going to form equilibrium, you're not. You're driven so strongly towards those products, you don't have an equilibrium problem. So what we're going to do is the same thing we did in the titrations. We're going to say, hey, we've got a strong reaction here. This is a strong reaction. And so we're going to use ourselves a Brice table, B-R-I-C-E, right? Before the reaction, our initial, then our change, and in our equilibrium. And we're going to run that strong reaction first. The first thing we need to do is convert from molarities to millimoles. Why? Because our volume's changing. We're diluting this stuff. So we could do it two ways. We could calculate the diluted concentration, or we could just convert to millimoles. I'm going to convert to millimoles first. So how much iron 3 plus do I have? And you're like, you don't have any, Professor Clemens, because you have iron 3 nitrate. All nitrate ions are soluble. 1 iron 3 nitrate produces 1 iron. So I've got 0.020 molar times 100 milliliters, and that is going to be 2.0 millimoles. Only two significant figures. And then for my cyanide, again, Professor Clemens, you don't have any cyanide. You have potassium cyanide. All potassium salts are soluble, so I have potassium ions and cyanide ions in a 1-to-1 stoichiometric ratio. I've got 1.0 molar times 100 milliliters, and that's going to be 100 millimoles of my cyanide. And so I can start to use that in my Brice table. And again, for the complex ion formation stuff, we always start with the ions, and then we make the complex. And some people ask, oh, how do we know it made iron with 6 cyanides? Because if you actually start to see some of these problems, sometimes it makes 4. Sometimes it makes 3. Sometimes, why? Well, it turns out most things make 6, but some things make 4. How do you know? Because you look it up in a table. You don't have to memorize anything about these. You have to get a table out and be like, well, I've got some nickel and I've got some oxalate. What does nickel and oxalate do? And you find it in the table. Oh, it makes 4 or it makes 6 or whatever. Just find it in the table. You don't have to memorize or try to figure that out. That is not pertinent to this class. There is some chemistry that you can think about that can help you with that, but we're not going to go over it. So we're just going to start with that. We're going to do our BRICE table before the reaction, the strong reaction, then our initial, and then we're going to do our ice. So before the reaction, here we got 2.0 millimoles, and we've got 100 millimoles, and we've got none of the complex because we haven't run our strong reaction. This is a limiting reactant problem. What are we going to run out of first? The thing we have 2 of, the thing we have 100 of. Hopefully you came up with the thing we have 2 of, minus 2.0 millimoles, minus 2.0 millimoles, just like that. Yeah, just like that. No, why not? Because I've got that factor of 6 here. I need to take into account that factor of 6. So it's 6 times 2.0 millimoles. And here we've got 1-to-1 stoichiometry, so I make 2.0 millimoles. So my initial is actually going to be 0 of this. 100 minus 12 is going to be 88 millimoles of this, and 2.0 millimoles of this. Now you remember, oftentimes we do the BRI part in millimoles when we've got volume changing, but in an ice table, it's really nice to have molarity, so we're going to convert this back into molarity. We're going to have 2 I lines. This is just converting into molarity. How do you convert into molarity? You divide by the total volume. So each of these is going to be divided by 200 milliliters, and I still get 0, and I get 0.44 molar, and I get 0.010 molar. All right, so now I can do my C and E. Remember, anytime we have 0 of something, the reaction has to go towards the 0. I can't have my reaction go to the right and form X of my iron cyanide complex because I don't have any iron. I can't make more of that. So anytime we've got 0 of a reactant or a product, the reaction has to head towards that thing that's 0. So I'm going to put an X here. Do I put an X here or do I put a 6X, right? Always that stoichiometric coefficient in front of there, minus X, because I know it's going to the left. So this one's easy. X 0.44 plus 6X and 0.010 minus X. Let's plug that into our K expression and then see what we can do. So KF is 2 times 10 to the 43rd, and that's going to be the concentration of my iron cyanide complex and my iron and my cyanide to the 6th power. I plug in my equilibrium value, 0.010 minus X. Iron is X, and this one is 0.44 plus 6X to the 6th. And that's equal to 2 times 10 to the 43rd. Well, what do I have? I have a 7th order equation. Most of you don't know how to solve a 7th order equation. Of course, you could put this into a solver, but I don't want you doing that on tests and quizzes. So how are we going to solve this? The only way we know how. X is small. Is X going to be small? You're like, no, X isn't going to be small. Look at K. K is huge. Well, if K is huge, right, means we should have a lot of product. But what is X? X is the amount of reactant we have. It's the amount of iron that we have left. Do we expect X to be small? Yeah, because K is so large, we're favoring the products, not the reactants. So we're going to go ahead and use the small x assumption, and you're going to see just how good the small x assumption is in just a moment. So small x assumption, 2 times 10 to the 43rd. What is a small x? It says anytime you're adding or subtracting x, it's insignificant. And so this is going to become 0.010 over x times 0.44. People often forget to keep that 6 there, to the 6th power. Boy, that's not too hard, is it? Right? In order to solve that, I multiply both sides by x. I divide both sides by 2 times 10 to the 43rd. I get x equals 0.010 over 2 times 10 to the 43rd times 0.44 to the 6th. Plug that into a calculator, making sure you're typing in the scientific notation right, using parentheses as need be, or whatever it is. And what do you get? You get that x is equal to I wrote down a number, but I don't like the number that I wrote down. So let's go ahead and just type that in my calculator. 0.010 divided by 2 times 10 to the 43rd divided by 0.44 to the 6th. All right, that was fine. It is 7 times 10 to the minus 44th. Minus 44th. Right? Which means my iron concentration is 7 times 10 to the minus 44th molar. That's a tiny number. That is the tiniest number you will ever run across. Okay, if you convert that to molecules per liter, right, you're going to multiply that by 10 to the 23rd. You're still going to get 10 to the minus 20th molecules per liter. You need to have 10 to the 20th liters to have 1 molecule of iron that's free. Crazy. Crazy small numbers. So you can see just how amazing that large KF value is. Okay? Now, is this useful for anything? Well, what do they do in spy movies? Right? In spy movies, the spy gets caught. He doesn't want to tell all his secrets. And so what does he have? He has a false tooth and he bites it down. And there's cyanide in there. What does the cyanide do? It goes into the bloodstream. It attacks anything with iron and attaches so strongly that there's no free iron left. So what in our body has iron? Right? Our hemoglobin. Our hemoglobin has iron centers that coordinate to oxygen molecules to bring oxygen to the rest of our body. And what does the cyanide do in there? It comes, it binds so tightly that nothing is getting that cyanide off, including oxygen. And so oxygen can't bind to your hemoglobin, which means you can't get oxygen to your body, which means you die. Okay, so that is why cyanide is used as a poison, because it's extraordinarily effective because of that K value of 2 times 10 to the minus 43rd. You're going to get 10 to the minus 44th molar concentrations of free iron left. Whoa! Amazing. Really, really amazing stuff that you can actually calculate numbers like this. They're almost meaningless. I mean, that number is so small to be almost meaningless. It just says there's none. I mean, there is no free iron in there. It's a number, but it's such a small number, it's essentially 0. So cool. All right, complex ion mixtures. Like, hey, let's take this complex thing and let's make it harder. Yeah, let's do that. Okay, what do I mean by complex ion mixture? Well, let's talk about iron 2 carbonate with a KSP of 2.1 times 10 to the minus 11th. So fairly insoluble, right? It's got a moderate solubility. So if you were to do the calculations, you'd find that the solubility and the concentration of iron in pure water, if you added some iron 2 carbonate, would be 4.6 times 10 to the minus 6 molar. Now, what if you wanted to try to dissolve and get more iron carbonate to dissolve in water? Well, we know one way, right? Would we add a strong acid or would we add a strong base? Which one? Hopefully you came up with, let's add a strong acid. Why? Because the acid would add to CO3 to make HCO3. And HCO3 is not part of this equilibrium, so that removes CO3, driving the reaction to make more. So that's one way, is right? Adding a strong acid, we can absolutely do that. But what if, on the other hand, we added some cyanide? What happens if we add some cyanide? Well, what did we just figure out? We figured out that iron, when you put cyanide, can make that iron cyanide complex with this extraordinarily large KSP, or KF value. Extraordinarily large complex ion formation value. And what you get is essentially no free iron left. So when we write this FeCO3, solid goes to Fe3 plus, oops, sorry, that's Fe2 plus. And CO3 2 minus, right? And these are both aqueous. In the first way, when we said, hey, let's add an acid, we'd be removing CO3 from our thing, driving the reaction to the right. But if we had cyanide, now in the last one, we had iron 3 complexes, and so it had 1 K value. It turns out for iron 2, what you get is combining with 4 cyanides to make that complex, and your KF value is about 10 to the 35, so still extraordinarily large. And so what's going to happen in this case? If we add some potassium cyanide and add cyanide to this solution, it's going to react with this guy, making this complex with a K of 10 to the 35. It's strongly driven towards the products, right? There's not going to be any iron left. Well, if we take away iron, what does Latelli's principle tell us? It tells us that more of this is going to dissolve to make more iron. As soon as it dissolves, it's going to find more cyanide in solution, and it's going to make more iron cyanide complex. And that's going to take away the iron. And so it's going to dissolve even more. And we get that same effect we got by adding a strong acid, but in this case we added something that the iron can complex with, whether it's in this case cyanide, or you could add oxalates, or you could add ethylene diamine, other things that it tends to, molecules tend to complex with. Complex. And you can drive that solubility reaction to the right. We're not going to quantify any of this. It's just a qualitative thing that I want you to understand, which is this: the solubility of an ionic compound containing a metal cation increases drastically in the presence of an anion that forms a complex ion. Right, as soon as we added that cyanide, we increased the solubility of the iron carbonate complex so much that quite honestly, until we run out of cyanide, that iron carbonate is just going to keep dissolving. Okay? So we could dissolve all of it if we added enough cyanide. So our solubility was significantly increased, right? We dissolved all of something that was essentially insoluble, right? 6 times 10 to the minus third molar, or 10 to the minus 6 molar concentration, very, very small. Neat stuff, neat stuff. All right, your turn. What is the concentration of the cyanide ion in a solution that begins with 0.2 molar copper 2 plus and 0.2 molar cyanide? On a test, I would not give you this part in parentheses. I would expect you to go into your tables of data and look. Well, you're like copper and cyanide. I don't know what happens with copper and cyanide. Do they make a solid? Do they make a complex ion? What you do is you'd go look and you'd see, do I see copper cyanide in my KSP table? Yes or no? Yes, hey, it probably forms a solid. Let's try that out. No? Okay, it probably doesn't do that. Let's try complex ion formation table. And so we see, do we see copper and cyanide in our complex ion formation table? That's how you're going to figure out this problem. In this problem, because I have to give it to you, I'm not going to make you look stuff on the table. I'm giving you everything you need to know right there. I'm telling you, hey, let's look at that KF value of copper and cyanide of 1.0 times 10 to the 25th. Again, so your goal is to find the concentration of the cyanide ion at equilibrium. I'm going to kind of say that out loud, but maybe write that in, at equilibrium, in a solution where you begin with 0.2 molar of this and 0.2 molar of this. So we don't have any volumes changing in this one. We're not adding solutions. I'm just telling you the initial concentrations of both of them. All right, go. Yeah, did you go? Okay. I know some of you don't want to. You should. You really should. How are you going to learn this stuff is by practicing it. If you're not practicing it, you're not learning it. So you thought the video froze, didn't you? Okay. Here we go. So what are we going to do? We're going to set up our complex ion formation problem and do our Bryce table, right? BRI. We have to do the strong reaction first. BRICE. So what's our complex ion formation? It's going to be the copper 2 plus, and it's going to be 4 cyanides, making our copper cyanide complex. And we know our K value is 1 times 10 to the 25th. Our BRICE, our before is 0.200 molar. This is 0.200 molar. And this is none. You're like, hey, we've got equal concentrations. Aren't we just going to, use up all of it or whatever? And we don't have a limiting reactive problem. But remember, you need 4 times as much cyanide as you need copper in order for the copper to react. And so it turns out we will run out of cyanide first. And so we're going to subtract all the cyanide. How much copper do we subtract? We're going to subtract off minus 0.200, divide by 4. That's the stoichiometric ratio, 1 copper to every 4 cyanides. And this one we're going to say, well, also 0.200 divided by 4. And what does that end up with? That ends up 0.2 divided by 4 is 0.05. Subtract that from 0.2, I get 0.150 molar. This one I get 0, and this one I get 0.050 molar. Which way is it going to go? Which way is it going to go? Anytime you have a 0, it goes that way. So I know this is going to be an x, and it's not just going to be an x, it's going to be a 4x. And then that's got to be an x there. That's got to be a minus x there. Our equilibrium 0.150 plus x, 4x, 0.050 minus x. We set up our K expression is going to be the concentration of copper cyanide complex over the concentration of copper, concentration of cyanide to the 4th, and that's going to be 1.0 times 10 to the 25th. And that's going to look like this, 0.050 minus x, 0.150 plus x, and 4x to the 4th. I just remembered in my previous problem, I did not check my assumption, but I can tell you that an x of 10 to the minus 44th is definitely smaller than anything we were subtracting it from. But you should check your assumption. I forget all the time too. It's really easy to forget because you're like, hey, I got my answer. But you got your answer by making an assumption, right? You just got to always check that assumption. All right, what am I going to do here? This is why I thought of it, right? Small x. Why do I think of small x? Because I have a really large K, and x is talking about reactants. A really large K really favors products. I'm not going to have many reactants, and so we expect x to be fairly small. So what do I get? I get 1.0 times 10 to the 25th is equal to 0.050 minus x is approximately 0.05, 0.150 here, and 4x to the 4th still there. So what do I get? I get that x to the 4th is 0.050 over 0.150 times 4 to the 4th is, my brain is figuring out what 4 to the 4th is, and it's not at the moment. 4 to the 4th is 256. I knew that. And then we got our 1.0 times 10 to the 25th. So if you do the algebra, it should look like that. Take the 4th root of both sides, and you get that x is equal to 1.07 times 10 to the minus 7th. X, was that the concentration we were looking for? Let's look it over here. X, we were looking for the concentration of cyanide. No, concentration of cyanide is 4x. And that's going to be 4.3 times 10 to the minus 7th molar. Woo! Let's scroll back up. 4.3 times 10 to the minus 7th molar, D. If you answered the 1.1 times 10 to the minus 7th, you got really close. You just forgot that stoichiometric coefficient there of the 4x in that equilibrium line that you really had to have. All right. So again, very, very small values, times 10 to the minus 7th in this case, not 10 to the minus 44th, but still very, very small values. Not much of that stuff remaining at equilibrium. All right. That is the end of our aqueous ionic equilibrium chapter, other aqueous ionic equilibrium. Hopefully you learned something about solubility, about precipitation, and about complex ion formation. Thanks so much for listening and have a wonderful day.